好，那我们接下来再进行今天下午最后一个 session。好，走。
Yep. Okay, so we have 2 more topics. Each hour of them are very short. The first topic is security of the neuromorphic computing. I know a lot of people trying to do this research on this neuromorphic, deep learning acceleration. But security of the neuromorphic computing in general, deep learning is also a very important topic. We just give one example, but there are many other examples here. So the first, let's talk about what are the major attacks of the machine learning. Number one, for the quantitative attack, which infer the learning will control all the training data. So it basically requires access to the training data. That means you don't have to fully control the data, but you may insert some poisoning data. Another one is called the rotary attack. Basically, generate the misclassification but do not affect training. There were 2 types of attack. The first one, quantitative attack. The one representative mechanism called the poisoning attack. The poisoning attack is very simple. You have some training data, as we just showed there. That data will be sent into the machine learning models and train the model. And the model can classify some objects. However, if you can somehow inject some bad data with some poison data, then you affect the accuracy of the model. And the percentage of this poison data does not need to be very high, like 1%. Some things are already enough to mislead the model. Here's one example. Say we try to recognize statin in amnist. So amnist, so we can recover this the image I will show here. However, if we apply the poisoning attack on this training data, we can see the restored the character become much more blurred. So actually means the higher vector is lost. Okay, the classification error, the validation error can be very big. Then after the testing error going to increase because the number of iteration increase. And if you inject some percentage of the poison data, you will see something like this. Okay, the second one is for E4 rotary attack. The example is called the underwater example. I was trying to find a video for you guys, but I couldn't find my video on laptop. So I have this image. The idea is very simple. In this underwater example, we have original image, and we all know the deep learning network is actually doing nothing else, but you can give the input data. We can categorize this data based on the decision boundaries built on this neural network. However, if we know that's going to be the mechanism, and we can add some small variability on this original image, we call the perturbation, and this perturbation will generate the perturbate, the image I show here, which is hard for you, to tell the difference between the perfect, the image and the original image. But this one actually going to dramatically, harm the confidence level of the original image from the panda to the gibbons. So that's one example. I have another video I couldn't find. You have a cup. Actually, that's a real video showing my student. You have a cup. And my student, paint some pen on top of this cup. And when you turn the cup, you will see the more and more, the pen show up on the front. And you will see the confidence level of the image classification will dramatically reduce from 99% down to 6 or 7%. And then the misclassified is cut down to cut to like the pencil box or something else. Even you can really see the cut. And the cut even have the handler on the side, so you know that's cut, right? Sorry, I couldn't find the videos of this, so I could not show you. So that's for the E4 rotary attack. So I give one example. That's for the learning attack. Learning attack is something like it's something like you have the drum. Like drum, we use the drum to do some spy work. And the drum needs to see some metering facility, take the image and put in the drum, and the drum sends the data back to the server. Or the drum can do some simple classification on this. But if someone captures the drum, and they may be able to recover the functionality of the AI states on the drum, even without physically access the chips. So how can we going to do it? Because we're able to replicate this models by input the fixed input to this drum and monitor output, and we can even train this our own the model to replicate the function of this AI state. So that actually make the machine learning model is supposed to risk of being attacked by the malicious users who have the physical access to the device, but now now can do reverse engineering on the system. So let's talk about the formulation of the attack model. Let's say we have some training data at the beginning. Well, then the training data is used to train the original model. Okay, and then we have input samples, and the input samples is going to generate the output of the test result. And originally, this testing data is used for the evaluation, so that we have some data which we can use either for the training or for the testing. But now, we generate some input samples, and we got the output in the testing result that creates like an I/O pair for the replication. And this I/O pair will be able to use to replicate the original model. That's the base idea. So even the attacker can submit any test samples, but the attacker cannot access the original training data, and the attacker has no knowledge about the parameter of the original model, but the attacker can still replicate this model. That is a base idea. So here's one example. Let's say we have a data set which is MNIST. Original model is SVM. And we usually use the different machine learning model. It's not deep learning model actually here. The K nearest neighbors, SVM or random forest, to replicate the functionality of the original, model. So the number of I/O pairs we need to train our replicate model is only about a couple hundred, not even 1,000, but we can reach the pretty much similar accuracy as the original SVM model, which we show here. And if the model you will use exactly is identical to the original model, then after about 800 I/O pairs, the functionality of this model will perfectly replicate the original functions. And even we use a different model, we can still reach pretty much the same similar accuracy. So let me explain why this is the case. It's very simple, because if an attacker can apply the input of his choice and observe the corresponding output, then the attacker can use this input and the output, which use as label to replicate the original model. And the training, the replicate model is very efficient, because this input-output pair already somehow be filtered by the original model. So this actually generates a much stronger information we can use to train our model. So that is the base idea. So how we can prevent people do this? So the solution is very simple. We need somehow to generate some mechanism to prevent the attacker from obtaining sufficient number of these equal output pairs to train their model. That's a very simple idea. And by doing so, we have a couple sub-solutions. Okay, number one, we may be able to generate some degradation, automatically degradation mechanism of our original model, so that our model needs to do periodical calibrations. For example, after we use 1,000 times, this model will not be able to produce the accurate output. So we have to somehow recalibrate our model. So if the people capture our model, they are not able to generate sufficient number of the accurate I/O pairs for them to train their model to achieve very high accuracy. So as I will show here, okay. Increase the number of the I/O pairs actually will dramatically reduce the accuracy. In reality, we want to see the super nonlinear curve like this, so that in reality we always see the curve like this, so that if we really implement such a degradation mechanism, then starting from using this input data, the accuracy will quickly reduce, and then becomes the degradation rate will become lower. It's not what we want, because we want to have some very accurate some very high accuracy at the beginning of the usage, and after that we see the degradation. We don't want curve like this. Instead, we want something like this. So which means at the beginning of the usage of the model, we can always produce a very high accuracy. And after a certain number of the usage, if we don't do the periodical calibration, the accuracy will sharply drop, so that you will not be able to generate sufficient number of all the I/O pairs. That is something we want. But the issue is how can we really design the hardware to implement such a degradation mechanism, but not the linear one, not this non-linear one. So that is the issue. Any questions so far? Okay. We'll go back to some device called the Memristor. Okay, this is the only device I have to talk about today. I think people will talk more, on the coming Friday. So the Memristor is an emerging device. Very likely the metal oxide device whose resistance can change when we apply the voltage or the current on it. Okay. And because the resistance of this device can change, so we can use this device as a symmetrical weight. So we can program the resistance of this device to represent, the symmetrical weight, and we apply the voltage, and the voltage will, what you apply on this device will generate a different current, and this current will represent pretty much the product between the voltage and the conductance of the device, right? So, but there is one issue here is, the Memristor device have two phenomena. The first phenomenon is the resistance of this device will slowly change because of retention issue. So which means if you put data there, if you don't touch the data, the resistance may change all over time. But more important, the device has some mechanical rate-induced change in the resistance, because if you want to raise the resistance of the device, the only thing you could do is apply the current and monitor the voltage, show up at the two ends of this device, or apply the voltage, monitor the current. But no matter what, you need to apply the current on this device, and this current will change the resistance of this device. So you will see the slowly change of this device. It's bad for this device, you use as a memory, but it's good for us to implement the automatic degradation of the neuromorphic computing things. So why we can do it? Because if you apply the voltage on the device, and the voltage is very small, then because of the exponential effect of the voltage reduce the resistance change, you will still be able to see the such a linear increase over time when you just apply the different voltage or the current over on this device. However, if you apply the very large voltage, you will see the exponential increase on on the resistance of this device. It will give us some hint. The hint is this. We may be able to use this technology to implement the automatic degradation of the resistance of this device, actually the shift of the device, so that if we don't periodically calibrate the resistance of those Memristor device, just apply the current to implement the computation operation of this device, then we maybe sooner or later the resistance shift of this device will become so large so that we're not be able to implement those. We're not be able to get the vector output I will show you. And this one shows the deviation of the conductance. You'll see the similar result. Go back to how we can implement the neuromorphic computing stuff or deep machine learning acceleration by using the Memristor device. I give a very brief introduction here. So the basic idea is you want to have the output. The output has the sum of this input and the weight, and this Z is the activation function of the Y. So this is a neural network with the input, output, and so on first. So we have the Memristor crossbar structure, which is very similar as we saw in the IBM tumors. So all the input are connected to all the output, and at each cross point we have one Memristor device. And remember, this resistance of this device can change when we apply the different voltage and the current. And we can have the voltage apply on all the input neurons, and all the current flow out of this interconnect underneath each device will represent the product between the voltage and the conductance of the device. We can use this one to implement the vector matrix multiplication with a very simple idea. Okay, now the question becomes how we can implement the neuromorphic computing system which we want. Here's one example. Let's say if we want to implement the neural network, which is a vector times by matrix, you need to have pretty much two Memristor crossbars. One represents positive, one represents negative, because you don't have the negative resistance of the device. Okay, so now I have two Memristor crossbars. And if I will have one voltage here, and this voltage will be applied to the input of the two Memristor devices. This is positive, this is negative, and it gets something out. And the delta W, which is the change of the weight, is actually the sign of this weight times by some gradient on the input. And when you apply the same voltage here, both the resistance at the corresponding position of both Memristor will change to the same direction. We don't like this. So we actually reverse the design. If you apply the voltage at one Memristor, you apply the negative value of this voltage to another Memristor crossbar. And the basic idea here is we apply the different polarization of this Memristor crossbar and we sum them as the input. Why we want to do this? Because we want to make sure if we have two Memristor crossbars on the first, we are able to apply the different polarization on this device so that the resistance shift direction of the corresponding position in the crossbar will be opposite. And why we want to have this one be opposite? Because we want to introduce a nonlinearity of the chain of the Memristor device. And here's the original design. So this basically shows the difference between the different weights. Now you'll see this one actually gives pretty much the small deviation between the shift of the Memristor resistance of this crossbar. And this one is this naive one, which means if I apply the same polarization on those two things, you will see some will be larger, some will be smaller deviation at the corresponding position, and reverse one that will be amplify the change of the Memristor resistance shift. Now you can see the larger and larger deviation between those two positions. This one to give us very high nonlinearity at each corresponding location. If you still remember what you learning from the middle school, if we have one parameters and both parameters change, if the direction of their changes are opposite, you will see the acceleration of this divergence. And that means the larger nonlinearity. If the change direction will be the same, then you'll see pretty much the linear increase between those two differences. So that is the basic idea we show here. Okay, so there are some benchmark we can do to test out and see if we're able to really improve the nonlinearity of this neural network. This image, the first with different training samples, evaluation samples. So first. Okay. This one for the digit, the benchmark, and the blue line shows the linear design, so which means the naive design. You see, following the increase of the number of the IO pairs, ICE, which is the difference between the output and also the target output, will pretty much linearly increase. There's a log scale. And for the nonlinear design, we will increase dramatically. But at the beginning of this increase of the IO pairs, they produce a similar the accuracy here. And the error rate, if we done error rate with a direct measurement of this design, you will see more clearly about the change. Okay. And obviously, the average curve, which is the nonlinear design, gives a higher nonlinearity on this. And the similar trend, can observe the thought and also the underneath or something first. Even underneath, actually see the nonlinearity design give us much worse, the accuracy compared with the linear one. So that may be the different benchmark, different response. So it's actually to solve the one problem which we have, because we have this opposite input, then we are able to improve the nonlinearity. But that's not enough, because we still see the large, the accuracy loss in some cases. Now the question is, can we really do a better job? We don't rely on this reverse input method that much, but still maintain the good nonlinearity. This chart shows the nonlinearity as it can be represented as a nonlinearity index, which is the product between the evaluation operation number and evaluation index, as shown here. Okay, so The gamma C and error rate, you can see, they have a different nonlinearity the index, and some are pretty good, the fault, and some are not. Some are not very good, like omnis, but still you'll see the significant increment between the reverse one and the naive one. So we all learned the Taylor expansion of the Taylor expansion of our the college math. And we all know the nonlinearity of the Taylor extension is if the delta 1 plus delta, if the delta is very small, you see the linear increase of the result. The first several order term, dominate the value. However, if the delta is very large, then you will see the very large nonlinearity of the curve. So if you understand this, then the question is the higher order of this Taylor expansion basically gave us a higher nonlinearity. So with the same philosophy, we found out that if you have more layers on your neural network, because of the cascading effect, you're going to see the higher nonlinearity as the response of the neural network. So here one example to show you have normalized IO pairs. At the beginning of the IO pairs, you see the very slow increase of the error rate for the 3-layer design. It's pretty much a linear increase on the 1 layer. But after that, you see the taking off of this error rate for the multi-layer design. This actually is the curve which we want, our green one. Okay. So in general, the depth of the neural network increase, you will see the improved nonlinearity of the degradation increase. If we combine those things, we find out that we can achieve the nonlinear curve, as shown here, which combines the reverse input and also the multi-layer design here. So if someone captured our drums and get our AI system and then send the input and got the output and use this input over here as a label data train is his own model, he's never reached very high accuracy because at some peak, the accuracy of the model will dramatically reduce because any data generated after this IO pairs will become unreliable data, as the accuracy of this data dramatically reduced. Okay, so we don't worry about that part. And similar, you can observe for all the different types of the benchmark as I showed here, from the digit, the font, image and omnis. And some of them are pretty nice, they are shown. However, if we don't apply the nonlinear design, so there's a linear design, you will see people are able to reproduce, the functionality of the original model. So that is one example to show how we can, how our proposed design, is more resilient to the replication attack, and how we can leverage, the nanoscale devices, our property to implement the secure, deep learning network. My student actually demoed another example which I did not put here, saying there is one company that spent $50 million to learn a model to dinosaur the debit, because they collect all the data to train their model. My student actually generate some fake data sent to their model and get the output. And he only needed 200 samples to replicate the accuracy which is about 98% of the original accuracy. So the company sell their service about $50 per sample to get some money, but we can reproduce their functionality with 98% accuracy by sending about 200 samples, which is about $10,000, and we can sell our own service like $5, so let's learn some. So that's one thing. So there's a robustness of our design because we worry about the resilience of our design to the process of variation of the Memristor device. We actually build these nanoscale devices which suffer from the process of variation, which means they have a deviation on the design parameters. So you're not going to change that much. If you precisely program the device, then you will not get one at all. However, the results basically show that our revised design is very robust to this process of variation, simply because of the nonlinearity heavily depends on the deviation of these properties at the two Memristor crossbars. So this process variation does not really affect this property that much. Another thing about overhead, because we need to periodically calibrate this system, right? So what is overhead to perform this periodical calibration? This result show that this is very small. Even compare, for example, the deviation about 5% when we do the calibration, or 10% we do the calibration. The percentage-wise, the cost is at most 20%. It's certainly an affordable cost for any secure system we usually use. Okay. So as a conclusion for this particular work, these results show that our design provides the better usability, especially nonlinearity against this replication attack. And the revised design has a much higher nonlinearity index, with about 180% increase on the MSE, and about 300% on the error rate. So that is one example about how our design for the security. But we have more examples in this year. Talk about other attacks. I put some microarchitecture work here for the deep learning acceleration, but more work will be given by Professor Lee on the coming Friday. But here, I just want to give you some basic idea about this microarchitecture. So there's one example we give is for the PipeLayer, which is one word we published last year at APCA, about how we can accelerate the convolutional neural network by using some Memristor device which we introduced. The convolutional neural network is basically part of the deep learning we talked about this one before, but we don't know if it's going to be computational or the memory intensive. Okay, we talked about the RM-based, for the Memristor-based acceleration, the capability to combine the computation and the storage and the process in memory to reduce the data movement. This is one example for the CNN. This is one example for the simple neural network. You see the input output neurons. You have active functions on first, and this is the RM-based crossbar structure, which we actually saw that in the previous slides. We have all the input, we have all the output, we have the Memristor crossbar in between that can perform the matrix on first. Okay. But previously, there are some papers talk about the similar ideas. For example, the chipping in East 2016 talk about they may be able to use in memory architecture for the RM-based design, so they can perform the method of vector multiplication here. And some other guys talk about similar ideas in East 2016 talk about this convolutional neural network. This one first. But they do not support neural network training. That's one thing. They don't talk about how to train the model. They also talk about inference. And some part of the deep pipeline we do the bubbles, because when you map the TNN down to those pipelines, for the different components, they actually have a different computation time, and for different layers, they have different size. So eventually, you are not be able to have a synchronized operation. There are a lot of bubbles, one layer, one component may be wait for another one first. Kernel mapping was not clear. Now it's very well, and a lot of digital converters may be needed because they want to convert the voltage with the floating, which is the analog value to the floating point value. Instead, we produce the PipeLayer. So this idea is we try to accelerate both training and the testing in our design. And we have intra and the inter-layers pipeline, and that's why we can always map the layers down to this Memristor crossbar. I will show you how to do it later on. And the spike-based input-output data that we showed before for the IBM tumors, so that it is also spike be able to perform the operation and also to integrating the output and generate the signal fire. So let's look at how you can do the kernel mapping. Okay, you have some modification between kernels and also the field of filters. And they have a 114 by 140 square here, and they have a 128 copies, and they have a 3 by 3 kernel. 3 by 3 filters, and they have a 128, another dimensions. We try to generate, the result I will show here, 128, 112, 112, and then you have 256 copies here. So what you do is first you need to convert this matrix down to the vectors here. Okay. The size of the vectors equal to 3 times 3 times 128. I will show you. Equal to 1152. Let's go back to this. Okay. And this one is prepared, for the multiplication, to this size. And then we also convert this 3 by 3 by 128 down to here. Because what we do is with the convolutional operation, we can compute this one with corresponding result here. And you can see we could come up this one down to this high bar to show here. Each of them is 1152. However, we have many copies here. It's over 12,500 something. Because if we really want to map all the data down to here, we actually generate a lot of copies. But there are so many redundancies here. So we actually have the data, we actually 3 by 3 filter moving out this the whole data map. And so to accelerate the whole thing, by assuming we have a large number of the R crossbar, we actually have this 1152 bars here, multiple copies on each cycles. In this particular case, we have the G times the 1152, and the G is the number we can compute in parallel. And here is 256. So if we define the 256, simultaneous copies, we need 49 cycles to finish all this computation. Correspondingly, because we want to support the multiplication of those 49 cycles, and for all this decomposed vectors, we need to copy the decomposed filters to multiple copies, and each all of them have the same the dimension as the yellow bar shown here, and we need 256 such we need 256, such a crossbar to finish the whole thing. And eventually we have 9 times for each column, we have 9 copies of those color bars, and then we compute this times all the copies needed to finish all the so to design the pipeline of this trading, that's about the forward operation. We have some data, and we go through the different layers. Here we use 3 layers as one example. So for the first steps, we actually compute the weight. And we compute weight again, and compute the final weight. We got output. And then we got output. We go back to compute what if the delta we compute and update the corresponding weight back to all the figures. So if you look at the condition of the pipeline, there are many data can be reused, across this whole DE1. For example, we don't need those data which are generated from output, to compute the output from each layer. But we do need this output, to compute the updates of this weight. So the computation of this update of the weight can be performed simultaneously with the layer operation in the forward part. And similarly, we'll do this second layer and the fourth layer. So now you can see we basically have a symmetric pipeline and folded them into the upper component and the lower component. And we perform the operation on each layers, including the forward and the backward simultaneously, because we know they're not going to share the data and simultaneously update them. There are no data on say things usually. And the pipeline like this. Okay, so we have A1, A2, A3, and A4, so on first. And after some computation, we have this A31, which is 2, and actually it basically means the forward and the back and backward. So as we show here, there's a forward, there's a backward, there's a one batch, so on first. And the reason we can do this, another thing is, we don't have to wait until the first batch to finish. And instead, we can have the corresponding pipeline, computation. So the final latency of the whole things will be similar, but the throughput will be much faster than the previous two. Because for each cycle, we're able to compute, we're able to compute, we're able to compute some part of the batch here, rather than we finish all the batch and go back to the so another thing about the resolution, because we worry about the resolution of the trading, you can still remind the case. In this case, we actually have the multiple arrays that represent different bits of the data. For example, the first bit represents the bit from 0 to 3, and then from the 4 to 7, or so on the first. And by doing so, we're able to use multiple copies to represent different bits. So eventually we can merge the data to the high precision result. And for the other data, we do similar. We give different weights on the different bits so that we can restore the long worth of the data. The result is here. So the green bar shows the GPU. It's basically normalized the performance. And the pipeline with PipeLayer without pipelines, which means we have all this mapping mechanism of the R and crossbar, but we don't pipeline the forward and the backward, so we don't run them simultaneously, and don't allow the part of the batch to send into the Pi1. Is the light blue one show. We see some improvement, but not as significant as the full solution, which have both the mapping on the R and crossbar plus the Pi1 result shown here. Yes. We actually wrote our simulator by ourselves. Because if you look at the computer architecture conference, there are no popular simulator for those things. So every group they run their own. They basically wrote their own simulator, similar such kind of result. So another question: how you can validate the result, right? So you have to compare your result with the previous design. So they show the similar results. So you know your simulator basically was reasonable comparison.
So do you try a very low level what kind of structure
That's a C code. Yeah, C code. Yeah. We just because in this case, for example, we don't really in this case, for example, the GPU one from the environment. Okay, so in this case, actually, we don't really have adding like a simple scalar or Yiran file or something first. We actually it is a dedicated Pi1, so you have to write your own simulator later to calculate how many cycles you need, and recycle what jobs you are doing here. So, in general, you'll see the compared to GPU, we see the speed up about 40 times, the maximum 100 times, energy about 7 times, and the maximum 70 times. The reason you are not going to see the similar energy saving on top of the speed up, because you have a large redundancy in the R1-based design. This one about the Reno is another word saying you have to design our neural network. You have to design the network on chip. So basically, you can guide the data movement on the chip to accelerate the design. For example, you have some controller. We have a sequence of buffer to get the data movement across the different Memristor R crossbars. So they can map the large neural network down to the multiple R and crossbars, or you can map the multi-layer neural network to those Memristor crossbars. And the first thing you do when you are using this design, you have to reconfigure all these routers to guide those data movement dynamically. And then the data will be sent into this hierarchical design to the different R crossbar or crossbar, and send them back, and then to read out to the other memory crossbar which already programmed it, or send them out to the main Pi1 some first. And we created our compiler, which can really identify the segment from the code, and then generate the instruction flag to move those data to the different components. A lot of people already done this actually. The similar things, and then you can accelerate the corresponding segment of this. The result basically show you can have similar the 100 70 times speed up from the first or the energy with some degradation. Because a lot of you mentioned this. If you consider process of variation of the RM design, will not be able to perfectly map. You still have to wait to this device. You'll see some degradation, but that's okay. And another thing is if you don't use a multi-layer substrum design, basically use some other design like associated memory which can absorb this variability, then you can improve the accuracy. So as a summary for today's talk, I think we have about 15 minutes to finish. We introduced the history about neural network, very briefly. And the comparison of the training algorithms, so many ones, distributed ones to the PC, compared to mainstream deep learning platforms, review the technique of the model simplification and reduction as the main part, and talk about the quantization allows for the IBM Turing chip, and all of them are based on the modification of the loss function on the internal stuff. Give some idea about the security of the neuromorphic computing, and give some review on the pipeline RM-based accelerator for deep learning. So we'll learn how we really map those neural networks down to the smaller scale in hardware sort of first. But this is just initial of the results. And more detail will be given by Professor Lee in the coming Friday. Well, originally she scheduled about 6-hour talk, start 5-hour recorded, but not down to the 3 hours something, so I can cover part of her work here. I think we just stop here. I don't have more slides to show. So any questions you may have? I think you're possible. We have some small scale circuit. Actually, some of the collaboration work has been done with modified. But we have never integrated this one with conventional pipeline or so. But for the broad process, we have done some work.
Questions? 有没有什么问题？ Okay, I have questions now. Maybe like a bit more general. Could you give an overview about how the AI projects going in US, in university, or from several government support project? Give us some overview because many audience come from different background and maybe they can give them a trend that what the research topic are working on different university or different group, and maybe they can find some interesting role model or something to follow up.
Okay, it's a very big.
Okay, it's a very big question to answer. Okay,
so number one, almost every top universities are participating in this kind of research on different angles. Okay, so if you want to participate in the research, we can mainly participate into 3 types. One is software and algorithm, one hardware, and one is applications. Application is very big, so that's very hard to comment because before deep learning, when we are doing the computer vision, those the pattern recognition, those kind of things. So people have very different techniques. Find the features on first, or the video or the audio processing, for example, natural language processing. But after deep learning was invented, we quickly convert to deep learning and we totally forgot any other techniques. So now if you go to their conference, no matter the NLP or or CVPR, they all talk about the deep learning, no others. So it's good or bad. And the good thing is, the reason people use deep learning because deep learning achieves the very high accuracy, which we never reach by using any other technique. The bad thing is we pretty much lost the variety of our research, but not everybody jumping to deep learning at that period. So that's the bad thing. Nothing's new. Okay, no matter deep learning or deep learning accelerated neuromorphic, people have done those things a long ago. So even we are experiencing another wave, that does not mean those things are new. It's actually have been there for years. But of course, we have very different understanding of different implementations. But the concept was there for years. In terms of the hardware, there are also a lot of debates. For example, one debate is about shall we use the conventional CMOS technology or we use a new devices. Depends on who you are talking to. They have very different answers. I just attended the DRC Design Research Conference last month. So you want to attend a panel with my advisor, same panel. I got a chance to say no. I did not. So we all agree. Okay, the new device will be very important, for this new AI hardware, because we can see pretty much the limitation of the current CMOS technology. But we all agree the current device research is not enough to support our ambition. Okay, that's one thing. One example is a new memory device like the Memristor or the R1 or the ST-ET1. People come up with a lot of circuit design to implement this acceleration. Most of them are analog computing, but there are many issues that people have not been solved. Not even talk about the device yield or so on first. Let's talk about the fundamental computing paradigm, such as shall we use analog compute, right? And what's the robustness of those things? Should be the spiking or should be the analog, should be so on first. That's what I see. Another thing is also people talk about if they want to use conventional computing or the spiking base. Because a lot of people are trying to say, the neural network is putting two parts. One, the ANN, artificial neural network, one, the ICNN, spiking neural network. It's not really true, because ANN is a much broader concept than ICNN. However, ICNN is closer to biological behavior of the human, neural network. So people believe that may be the future trend. Yes or no? Because yes, it is a spiking, has so many mechanisms you can leverage, to encode the data, such as amplitude, such as frequency, such as the temporal relation between different spikes. Okay, this is much richer than the binary representation. That's for sure. The bad thing is the spiking is very hard to control. For example, a lot of people ICTDP, which has a temporal relation between different spikes. But if you want to precisely control the temporal relation between spikes, it's very hard in the integrated circuits. So we don't know yet. Again, people have a lot of debates, and we don't know what is the answer. And also spiking, the researcher in the spiking-based solution have not come up with any efficient software or the algorithm which can be implemented on the CMOS or the circuitry. That's another issue. So we have no evidence to show this. Okay. But we cannot say they are wrong because we just because we don't know. On another side, for the CMOS part, people also implement a lot of different design, and also that is intention for another debate in the deep learning society, which is shall we do the neuromorphic or we do the deep learning acceleration? If you look at our terms, I differentiate them because neuromorphic is what called the bio-inspired computing. Because they believe they learn from the biological system. But deep learning is another side. I have no understanding about the biological system. I have no understanding even the math background of this part. It just simply works. And now we talk about the engineering work, how we can accelerate those stuff. Right? And the deep learning guy does not believe they benefit from the neural network guy. Okay, so that's another thing. Okay, fine. If we consider this debate, so go to the CMOS part, there are also two different components. One is the neuromorphic. We'll say the tumors. So I have a spiking, approximate computing, and this stuff. Another one say I don't care about this. I just simply accelerate CNN, RNN, or any particular application. I just understand the data flow. I just accelerate them. Whether they have a biological background, whether they have a neural network, math background, I don't care. So that's why you see they publish in the different forums or they compete each other. But again, we don't know. They may merge or they just compete each other in the field. I forgot to mention actually, there are some researchers in Georgia Tech actually they're also doing a floating point gate, right? Floating gate, so they implement they use the floating point rather than the R1 or spintronic device to represent the data. That's also one way to do. It's a sort of conventional CMOS, but the philosophy very similar to the emulsion device. That's another thing. That's all the hardware device. So for the software design, they're very diverse. They have very different services. The deep learning gives IML. For the neural network, they have IDCA and so on first. Again, they fight each other. So the deep learning guys, you don't take much. Deep learning guys don't benefit much from you. Neural network guys say you didn't give us sufficient credit or something first, but that's fine. I mean, that's always such a debate on this. But there are a couple of things we don't understand that we actually many people are focusing on is unsupervised learning, because supervised learning has been done. A lot of unsupervised learning is very hard, so we don't know what would be the good solution. But good part you want to learn is a GAN. So GAN generative adversarial network. I mentioned a little bit in my talk. So that means you can generate your own training data and learn by yourself. You can generate the fake sample and learn from it. So that may solve the unsupervised learning issue, because if you don't have sufficient data or labeled data, you may be able to learn from it. Another is about security. So you can generate the fake things which can mislead our model. So how you can design the intelligent neural network to differentiate which one is the fake one, which is not fake one. This is the issue. There are so many things which we're doing now. We actually, every single paper with the public top conference saw very little things actually. So there's so many fundamental things we don't know, and we still are working on those things. And any technology advances on the software or the algorithm will quickly be reflected by the hardware design. So that's why if someone say, hey, I'm the circuit designer, I want to design an accelerator, you need to learn software. You can, or the algorithm. You cannot just say, I'm a good circuit designer, I will design something that will be useful for those guys. It's very hard now. I'm not sure if that's
So, any questions? No? If not, we will have a gift for the speaker. Okay, so this concludes today's talk. 我们用最热烈的掌声谢谢 speaker。